In this video, we're going to look at some key patterns that you can derive from looking at the Bohr models of the atom of the first 20 elements placed in the periodic table. So what you're looking at here is the Bohr models for the first 20 elements. And what we want to do is see if we can see any patterns in terms of how the periodic table is organized. First of all, in terms of terminology, this is a column, and our column is our group of elements. And then when we're going this way, these are our rows or our periods. And the reason they're called periods is because what we find is that there is a pattern in the periodic table that repeats itself periodically. So if you lined up all the elements in a big long line, you would then use the pattern that you're seeing to create the periods or the rows as the pattern repeats. Okay? So let's first look at the periods and just look at a glance what the things in the same row have in common. The hydrogen and helium, you can see they each have their electrons on the first shell. The second row, you can see that they all have a full first shell, and then the second shell has a particular number of electrons in it. We're increasing as we go across here, but they all have a total of 2 shells. In the third row, you can see that the atoms have a total of 3 shells. In the fourth row, you can see that their electrons occupy 4 shells. So there's one pattern, right? When we're looking at the summarizing here, the number of energy levels in an atom is going to equal the period number. Okay, so you can look at an atom anywhere on the periodic table and you can predict how many shells it will have. So if I just give you a separate example, if you look at a periodic table and I asked you for the element iodine, how many shells it will have, you can count. It's in the 1, 2, 3, 4, 5th row. So you could report that you expect it to have 5 energy levels. The other pattern that we want to address here is the valence electrons. When we look at elements that are in the same group or the same column, you'll see that we'll talk more about this in a moment, but we call them families. And we call them families because they have similar properties, some similar chemical and physical properties based on their similar electronic structure. And what is similar about their electronic structure is how many valence electrons they have. So if we look at group 1 here, everything in group 1 has 1 valence electron. In group 2, everything has 2 valence electrons. Now we're skipping over our transition metals to reach the group with boron, and those ones have 3, and so on and so forth. I continue on. And so what this shows us is that we have this ability to be able to count the electrons in the valence shell quite quickly, just based on the position of an element in the periodic table. And this is going to be incredibly useful to us because instead of having to draw a Bohr model to determine those valence electrons and draw a Lewis dot diagram, we'll be able to just use the location on the periodic table in order to get that information. And this is going to be really helpful to us when we want to look at bonding. Because really, we don't need the entire atom when we're thinking about bonding. We're going to be focused on those valence electrons. Now, I'll just also address the question that you might have here about helium. So I sort of put an 8 off to the side. So the noble gases, neon and down, will have 8 in their valence shell. Helium has 2, but as you'll remember from the Bohr model, 2 is the maximum number of electrons that are typically found in the first energy level. Okay? So they do all have in common that their final orbital is reached its maximum number of electrons. Now, from this information as well, we can identify a couple of things. We can talk about the families. So I've already addressed the fact that we've got the rows and the periods. And this here is a summary of the different families that we reference in the periodic table. So this group 1, and just the red elements there, those are our alkali metals. The beryllium or group 2 elements, those we call our alkaline earth metals. Okay? And their names suggest alkaline means that it's basic, okay? So that it has a property that it's basic when it's dissolved in water, which is where it got its name. Now the yellow elements here are transition metals. The nitrogen and the oxygen groups, the nicogens and chalcogens, we don't often, I won't be asking you to spell those or to write those out. We don't use them all that often, okay? But it is helpful to see them. Our fluorine, chlorine, and so on, those are our halogens. And our final group here is our noble gases. The elements that are down below the periodic table are the lanthanides and actinide series. We don't typically work with these at all in high school chemistry. They're typically radioactive elements and pretty specialized, so we don't typically work with them, but we will talk about them from time to time. You'll notice that hydrogen here is not classified as an alkali metal because it is a gas and it's a non-metal. It's on this side of the periodic table because of its similar properties to the elements in that family in terms of its reactivity. So because it has one valence electron, it will react in a similar way to the other elements in the periodic table. Sometimes you'll see, and on the back of your workbook, you'll see that the hydrogen is sort of duplicated on this side because in some ways it can be thought of like a halogen because it could gain one electron to fill its outer shell. The other piece about the periodic table that you need to know at this point is how to identify metals, nonmetals, and metalloids based on the position on the periodic table. So recognizing that our staircase separates the metals and nonmetals. Okay? And for the most part, we're going to be really looking at whether it's a metal or a non-metal. We're not going to focus too much on the details of their metalloids. They're really interesting because they do have some overlapping properties. The other thing that is of note is that you should, at this stage in your science career, have a good sense of what are some of the typical properties of metals and non-metals. Okay? So their conductivity, how what they look like, that metals are typically shiny and conductive and they're malleable and ductile, whereas nonmetals typically are not conductive, etc. Okay, so do be sure to review those basic differences.